Okay, it's my great honor and privilege to introduce my friend and collaborator, Larry Guth. Larry came to harmonic analysis from differential geometry and armed with a unique perspective and original ideas. In just a few years, he's cut a big path through incidence geometry, harmonic analysis, and now analytic number theory. The conference organizers insist that I mention that in 2015, Larry received the Clay Research Award, and now he's going to give us an introduction to decoupling.
Well, thank you, Ned. It's a pleasure to be here. So I'd like to tell you about decoupling, a recent development in Fourier analysis, which I hope will be of interest to a broad audience. And I'd like to say at the outset that the talk is really for a broad audience. I'm mostly aiming at the people who are not harmonic analysts here. And I'll stop several times for questions, and so do let me know if anything doesn't make sense. Okay, so decoupling has applications to several areas and several old problems, and including some in number theory. And so the angle I want to take for the talk is to start by introducing some problems in number theory, and then explain how they're connected to Fourier analysis, and explain the new ideas that have helped to solve some of these problems. Well, the problems I'll talk about are about Diophantine equations. So the problem is, how many solutions are there to some Diophantine equation or system of equations? And so, for example, I'll start by describing a problem about sums of 3 cubes. So let's say that S of n is the number of solutions to this equation, a1 cubed plus a2 cubed plus a3 cubed is equal to b1 cubed plus b2 cubed plus b3 cubed. Okay, and here these numbers should all be integers. So ai and bi are integers. And they are in the range between 1 and n. Okay, so let's start by sort of guessing how many solutions we might expect this equation to have. So first of all, there are n cubed kind of trivial solutions when ai is equal to bi. They're n cubed, they're called diagonal solutions. ai equals bi. And the more interesting thing is to try to figure out how many non-diagonal solutions there are. So let me share some common intuition. So let's think about the left-hand side of this thing, a1 cubed plus a2 cubed plus a3 cubed. Well, we have n cubed choices for the variables. Okay, and then when we look at this sum, it's somewhere in between 3 and 3n cubed. Okay, so we're going to produce n cubed numbers that are in this interval, which has length a bit more than n cubed. And so the intuition is that these numbers should be reasonably spread out. So they should take about n cubed different values. And each value, it might appear more than once, but it's not going to appear a whole lot of times. The intuition is that it should be not that different from if n cubed times I just picked a random number in this interval and saw what happened. Okay, so we expect around n cubed different values. And we expect that each value has few representations. Each value occurs few times. Okay, and if you believe that, you can easily figure out how many solutions there should be to this equation. There are n cubed choices for the left-hand side. And for each of those choices, there are only a few choices for the right-hand side, but at least one, because the b's could be the same as the a's. So there should be about n cubed solutions to this whole thing. So here's a more formal conjecture. The number of solutions is at most n n to the 3 plus epsilon times a constant depending on epsilon for every epsilon bigger than 0. Actually, it's plausible that even stronger thing is true, that it's just bounded by a constant times n cubed. But even this weaker conjecture is far beyond anything that we can prove. So anyway, so we don't worry about making it stronger. Okay. So there's an approach to this type of problem using Fourier analysis. And the starting point of that approach, so here's the Fourier approach. So I define a trigonometric polynomial that's kind of tailored to this problem. The trigonometric polynomial is f of x is the sum of e to the 2 pi I a cubed x. And the sum as a goes from 1 to n. And then the claim is, lemma, the number of solutions of this equation is the integral from 0 to 1 of the norm of f to the 6th. So there's a cute little trick to check that this integral is recording the number of solutions. It goes like this. So proof. So the integral of f to the 6th is the integral of f cubed times f bar cubed. And all we're going to do is to expand out that integral. So go. So when I expand out f cubed, I write out each f as a different sum. So I have 3 variables, a1, a2, and a3. And then I multiply that all together. When I multiply them together, I get e to the 2 pi I. I'll have a1 cubed plus a2 cubed plus a3 cubed times x. Right, so what I've written so far is the integral of f cubed. And then f bar cubed we expand in the same way. So I'll call those variables b, b1, b2, and b3. And everything is the same, but because of the complex conjugate, they'll come here with a minus sign. Okay. And all of these things are going from 1 to n. Okay. We can bring this sum outside of the integral. So we have a sum of a bunch of integrals from 0 to 1 of this thing. And the point is that if this frequency in parentheses is 0, then we're integrating the function 1, and we get a contribution of 1. And if this thing in parentheses is not 0, it's an integer, and then this integral will be 0. And so when we add it all up, what we get is the number of times that this thing is 0. In other words, the number of solutions to my equation. Okay, so that is a cute trick, but it raises the question, did we actually make any progress at understanding how many solutions there are to the equation by writing it in this funny way with this function f? And this is not so clear. So let's start trying to use some things from Fourier analysis to estimate this integral and see what we can learn about the number of solutions to this equation. So let's start with some basic things. So let's call this first bounds. Okay, so one basic bound for the size of f is that the norm of f of x is at most n for every x. That follows from the triangle inequality. F is a sum of n terms of size 1. Okay, and the second fundamental thing, so we'll call this triangle inequality. The second fundamental thing is orthogonality, which allows me to compute exactly the integral of f squared. So the integral of f squared is n by orthogonality. The reason being that the integral of the norm squared of each of these functions is 1, and these functions are orthogonal to each other, and so we get n. Okay. Okay, so now we can combine these two basic facts to produce some bound on the quantity of interest. So proposition, the integral of the norm of f to the 6th is bounded by n to the 5th. So proof. Well, the integral of f to the 6th, I know that f is, so I'd like to use orthogonality, which is the deeper of these two simple things. So I'd like to involve the integral of f squared, but I have the integral of f to the 6th. So I want to get rid of the integral of f to the 4th, and I can do that by using my pointwise bound for f. So this is at most n to the 4th times the integral of f squared. And the integral of f squared is n, so this is n to the 5th. Okay, now it's worth saying that this is not a very interesting bound for our original problem. Here's a trivial proof that s of n is at most n to the 5th. So I look at this equation. There are n to the 5th ways to choose a1, a2, a3, b1, b2. And for each of those choices, there is at most one value of b3 that solves the equation. So that's the bound of n to the 5th. We proved it in a convoluted We've not yet done anything interesting, but this gives a little perspective. We can think, what would we have to figure out about the function f in order to do better than this trivial bound? Yeah? So I'd like to think of it this way. So suppose we have some function g that obeys the two bounds that we know. So g of x is at most n at every point, and the integral of g squared is also n from 0 to 1. So how might this function g look? There are sort of two extreme behaviors. One is the most spread out it could possibly be, the most evenly distributed it could be, and the other is the most concentrated that it could be. And they look like this. Cool. Okay, so there's an important height scale here. Let me make it bigger. Important height scale, which is the square root of n. And that's important because it's from an L2 point of view, it's sort of the average value of g from this. So if g was the same height all the way, or roughly the same height all the way, that height should be the square root of n. So the norm of g could look like this, and I'll call this the spread out case. And in the spread out case, it's easy to see that the integral of g to the 6th is like n cubed. So if our function actually looked sort of like this, then that would establish the conjecture. Okay, now what's the opposite of this? The function g could be sort of as concentrated as possible. So we're going to saturate this, so g at some places will go all the way up to n, and it's going to do that as often as it can, given this bound on this integral of the square. So that would look like this. So between 0 and 1, there are a few places where the function is quite tall. This is height n. And otherwise, it's small, maybe root n, maybe 0. And there's this red set where the function g is quite large. And the red set can't be too big because of this bound. So the length of the red set, the biggest it could possibly be, is like 1 over n. That's consistent with this. So we'll call this the focused case. Say that I would say informally that g is focusing on the red set. And in this case, it's not hard to check that the integral of g to the 6th is now like n to the 5th. Okay, so to do better than the trivial bound using the Fourier approach, we have to show that g looks more like this than like this. All right, now, so this opening problem, it was our warm-up problem, but it's a deep, unsolved problem of mathematics. We don't know how to do that. It's maybe worth saying that there are non-trivial bounds for this. There are definitely bounds that are better than n to the 5th, but they're not 3 plus epsilon, and there's no sort of plan in the works anywhere, no set of tools that seem like they could plausibly get to this 3 plus epsilon. Okay, but there are some other problems of a similar flavor where recently we've been able to get sharp estimates. And so I'm going to tell you about one which was conjectured by Vinogradov back in the 1930s. So here's the problem that he considered. Okay, so he considered a similar thing called JSK of M, which is the number of solutions to a system of Diophantine equations. So the equations are a1 plus as equals b1 plus bs. That's the first equation. The second equation is a1 squared plus as squared is b1 squared plus bs squared. And we do this k times. So the last of the equations is a1 to the k plus as to the k is the same as b1 to the k plus bs to the k. There's the number of solutions to this. And as usual, the ai and bi should be integers between 1 and n. OK. So you could make a conjecture about this by following the same reasoning that we used to make a conjecture about S of n. And the natural conjecture is the following. Conjecture JSK of n is at most a constant that depends upon s and k and epsilon, n to the epsilon. So this is our fudge factor. And then n to the s plus n to the 2s minus something. So it's very parallel. This n to the s is the number of diagonal solutions, which you can just see. If you set ai equals bi, for all the I, that's a solution, and there are n to the s choices. And this is a reasonable guess for the number of non-diagonal solutions that you can make by the same kind of heuristic reasoning that we used over there. OK. So here's something about the history of progress on this conjecture. Before Vinogradov, people knew the following. People knew that this was true when k is 2. And they knew that it was true when s is very large. So they knew it was true if s is bigger than 2 to the k. So one of the themes of analytic number theory at the beginning of the century was that if you take a system like this and you make the number of variables extremely large, as it gets larger, the system becomes better behaved, and it's possible to prove that naive heuristics like this are true.
That's not really the case for 2 to the k before Vinogradov.
Is there some other number I could put there, or really no one had thought about it?
Really not considered before Vinogradov.
OK, right. But let me put it this way. Would it be fair to say that if I took the relevant integral that I write down and plug in the Weyl differencing bound and estimate that we'd get it?
A single equation of degree k, a few years after Vinogradov, the 2 to the k bound, a single equation of degree k would be valid.
Right.
That was one.
OK. What did I say? OK, let me just cross this out. Let me say that Hardy and Littlewood thought about some problems about Diophantine equations, and they were able to solve them when the number of variables was much larger, was very large compared to the degree, and exponentially large compared to the degree. OK. Very good. OK. Thank you, Trevor. So Vinogradov proved that this is true if S is sufficiently large. And sufficiently large means bigger than something like 10. Maybe I'll write a constant. I'm not sure. So k squared log k. There's something I should maybe say. So to process numbers like this, when we look at an expression like this, it's worth thinking about when each of these two terms dominates. And so that just depends on how big S is compared to this. And so if S is bigger than k times k plus 1, bigger than k times k plus 1 over 2, then the second term dominates. So s equals k times k plus 1 over 2 is a sort of a critical value for this equation. And it's the most difficult one. It's not that hard to check that if we knew this conjecture for this value, then we could also establish it for other values of s. And so Vinogradov was able to prove the conjecture for s that are pretty close to this critical value, whereas what the techniques before, well, maybe not for this conjecture, but for some sort of similar problem, required extremely large values of s. Okay, and then in the last few years, the conjecture is true. So that's the progress, the recent progress. And it's due to two groups. One group is Jean Bourgain, Cyprian Demeter, and myself. And then the other group is, well, the other person is Trevor Woolley, who is correcting my history. And this approach uses Fourier analysis. It uses what's called decoupling. And Woolley's approach is different. There are a lot of subtle new ideas, but in some sense, it's more in the framework of Vinogradov's approach. And unfortunately, I'm not competent to say that much about it. Trevor gave an interesting talk about it and somewhat comparing the approaches earlier in the workshop, and I'm just going to try to explain the ideas of this approach. Okay. So one thing you might ask is, why is this conjecture more approachable than that conjecture, which is still wide open? It looks, if anything, more complicated. And Vinogradov's point of view about why it's more approachable is that it has more symmetry. So both systems are symmetric under dilations, which means that if I took all of the variables and multiply them by a number d, then one solution will turn to another solution. But this system has an additional symmetry, the symmetry under translation, which means that if I take all of the variables and I add to them some number t, one solution will turn to another solution. It's a little algebra exercise to check that that's true. So Vinogradov's point of view was to exploit, well, one of the ideas was to exploit that extra symmetry, and that makes this system more approachable. That idea is involved in all of the recent approaches, but it's going to be a little bit under the hood in what I'll talk about. Yeah? Okay, so my goal is to explain to you the ideas in this proof. And as a model case, I'm going to explain what happens when k is 2. Now that may seem a little suspicious because, well, I explained earlier, I just mentioned that k equals 2 has been known for a long time. It's much easier than the other cases. So let me tell you a little bit about the classical proof of k equals 2 for context. So the old proof of k equals 2. So here's a lemma that plays a big role in that old proof. If you look at the number of solutions to the equation a1 squared plus a2 squared equals m, then that number is pretty small. It's smaller than c epsilon m to the epsilon. And here's the proof idea for that equation, for this lemma. So the proof idea is that we can factor a1 squared plus a2 squared. So we have m is a1 plus ia2 times a1 minus ia2. And now the key input is that there is unique factorization. We have unique factorization in the Gaussian integers. So m has a unique factorization. It's written as p1 to some power times ps to some power. And a1 plus ia2 has to be a factor of m. So we must be able to write it in the form p1 e1 prime up to ps es prime, where the ei's are, ei prime is somewhere between 0 and ei. Okay. These aren't all solutions, but it's not hard to count this sort of thing, and that gives a count for how many solutions there could possibly be, and it gives this bound. So that's a very nice trick, but it doesn't work so well for studying cubes, for studying problems like conjecture 1, or for studying the Vinogradov conjecture when k is bigger than 3. And the problem is, so it doesn't work so well for cubes, The problem being that a1 cubed plus a2 cubed plus a3 cubed doesn't factor. So you could use an argument like this to say that there are not too many ways to rate a large number as a sum of 2 cubes, but it doesn't lead to sharp estimates for any of these problems. And the harder thing that one would like to know is that there aren't too many ways to write a large number as a sum of 3 cubes. But you can't do it by factoring because it doesn't factor. OK, so in hindsight, it may be a good idea to try to reprove this classically known thing without using this factoring trick. And so I'm going to explain Bourgain-Demeter's approach to reproving this thing without using any factoring. And it turns out that that method can then generalize to all of the case. It doesn't face any kind of barrier the way the factoring method does. Cool. OK. So then the other thing I wanted to say, so the proof I'm going to show you really is due just to Bourgain and Demeter. They had done the case k equals 2 earlier in a paper that I think was a real breakthrough. And then together we did some more technical version of that argument, which works for the bigger values of k. OK. OK, so we're going to pursue a Fourier approach to estimating these numbers. So just by the same technique that we did here, we can write the number of solutions as an integral of some trigonometric sum. And I'm going to describe it. So here's how I'd like to write it. So f of x will be a trigonometric sum with some frequencies called omega sub a. But the new thing that's going to be different is that we're going to get a k-dimensional integral instead of a one-dimensional integral. So if we look at JSK of n, that's going to be an integral over a k-dimensional cube instead of the unit integral. And the power here depends on s. This is the power 2s. And I'm just going to focus on the case k equals 2. And in that case, these frequencies, omega a, all lie on a parabola. OK, so let's make a picture of it. So here's my parabola. And along the parabola, I have these different frequencies. So these dots are the frequencies omega a. OK. So the plan is that we're going to, so we see this geometric structure that all of the frequencies are on a parabola. And the plan is we're going to try to take advantage of that structure and see what it has to say about the function f. There's a branch of Fourier analysis called restriction theory, which is concerned with this problem. If you have some function and you know that its Fourier transform is supported on a certain curve, like a parabola, then what can you say about that function in the x domain? And in particular, we'd like to understand, can it be very focused, or does it have to be more spread out? And we're going to get at that by a multi-scale approach. So we take this parabola, and instead of trying to add up all the frequencies all at once, I'm going to break it into some smaller pieces. So let's say this piece is called theta 1, this piece is called theta 2, and so on. And f sub theta j is the sum just over those frequencies that are in the arc theta j of our exponential sum, e to the 2 pi I omega a dot x. And then I'm going to take these short arcs, and I'm going to group them into longer arcs. So maybe this arc here is tau 1, and this arc here is tau 2, and so on. So f sub tau 2 would be the contribution to the trigonometric sum coming from the frequencies in tau 2. But another way that I could write that is f tau 2, say, is the sum over the thetas that are in tau 2 of f theta. OK, so does that notation all make sense?
What is W, did you tell us?
So WA is in fact just A comma A squared, where A goes from 1 up to n. Other questions? No? Okay. So there's some geometric information about each of these functions, f theta and f tau and so on, which can be described in terms of a tiling structure. So suppose I consider one of these thetas. So there's theta. It's a small arc of a parabola. And I put it inside of a rectangle. So the rectangle has some length L and some width W. And then there's a sort of a natural dual rectangle where the axes are the same, but the lengths of the sides are inverted. So it's called theta star. And it looks like this. So this axis is the inverse of the corresponding axis over here. So that length is W inverse. And this axis is L inverse. OK. And then we can tile the plane with translates of this rectangle. And an important lemma in the Fourier analysis approach is that the norm of f theta is roughly constant on each tile. So this is actually a white lie. The exact statement is a little more technical. But what everyone in the field likes to imagine as they're working out arguments is that if I take any 2 points, x1 and x2, that are contained in the same tile, then the norm of f theta at x1 is approximately the same as the norm of the f theta at x2, in the sense that these two numbers differ by at most a factor of 100. OK. So this isn't that difficult, and if there's time at the end and people feel like it, we can talk about why this is true. But the main thing I wanted to tell you today is about how this is useful for understanding the shape of f and bounding the integral of f to some power. OK. So I like to keep this picture. This is a one-dimensional picture, but it gives the idea. We want to understand whether f could be very focused like this, or whether it needs to be more spread out like that. And I want to explain how this structure of tiles has an impact on that question. OK. So we look at each f theta. And each f theta is somewhere on the spectrum between very spread out and very focused. And if we are so lucky that each f theta is very spread out, then that helps us. And it's easy to prove that f will obey a better bound than this trivial, kind of trivial bound in that proposition above. So the worst case, in some sense, is when each f theta is very focused. And that's the case where the tiling is going to help us. So let's suppose that for each theta, f theta is focused. So focused in a few of the tiles. So in a sparse set of the translates of theta star. OK. So I'm going to color code some of the thetas and think about what each f theta looks like. So maybe I'll start with this theta over here, which I'll color green. And that looks like theta 2. So in green, I'll illustrate these are the places where f theta 2 is big. Okay. So the tiles corresponding to theta 2 are pointing in that direction. So it looks something like this. Okay. So I wanted to pause here and check in. This is an important moment where people in my field are very used to drawing this picture and have and used to understanding what it means. I want to check in. Is it clear what we're talking about here? Yeah.
With the choice of, so you said like omega a will be a and a squared, but would a run from something like negative n over 2 to n over 2 if you have, like if you're on the other side of the graph?
Yeah, that's a good question. Right. So I said that a should go from 1 to n, and then I drew a picture where a appears to go from negative n over 2 to n over 2. That's right. So let me say that we could study a similar problem where just at the beginning I let my integers run from negative n over 2 to n over 2. And then I would have this picture. Or if I honestly talked about this problem, I should only really have the intervals from here to here. And
It's really the same picture, different coordinates.
yeah, it's really the same picture in different coordinates. That's right. That's right. And it's nice to draw it in these coordinates because we have more room to see the things that are going on.
You already told us that the Gromov equation is translation invariant.
And that's right. And the equation is even translation invariant, so we can shift it and nothing changes. Yeah, which is the same observation that Andre made. Nice. OK, good. Other questions? OK. OK, so let's think about a couple of other thetas. I'll make one over here that's blue and one over here that's red. OK. And following the pattern, I'll draw in blue the places where that f theta is big. That should be some rectangles that are vertical. So it'll be like this. And I'll draw in red the places where this one is big, which should be some rectangles that are diagonal in the other direction. Maybe like this. OK. Cool. So the point of this picture is the following. So we have an image of each f theta, and now we want to understand what happens when we add the f thetas together. And what we see here to some extent is that the f thetas are big in different places. And when we add them up, that makes the sum more spread out than it would be if the f thetas were big in the same place. So something like this blue thing by itself, is not a very good strategy for trying to make f focus. Because one of the f thetas is big here, the others are not big there, and so the sum is not going to be dramatically big in this region. So if we want to make a bad example, we would like to try to have each f theta very focused, and we'd like to have them all focused in the same place. But they have trouble cooperating to do that because their rectangles are pointing in different directions. So let's summarize the key point as follows. Key point is that the different f theta j are big in different places. That's because the tilings are slanted in different directions. And that's good because it forces f to be more spread out than is guaranteed by just triangle inequality and orthogonality. So this is the tool that we try to leverage in the decoupling approach to estimating these integrals. Okay. So let me say a little bit about the history now. This tool, the observation of this tiling structure and using it to try to estimate the norms of a function f that's supported on a parabola, that goes back to the 1970s, and it's been used a lot in this area called restriction theory ever since then. And so if 10 years ago you were described to someone in the field of restriction theory this plan of how to attack the Vinogradov conjecture, they would say, yeah, this makes sense. These functions f theta can't all focus in the same place, and we should get some improvement for that beyond the trivial bound. But it doesn't sound very likely that this approach could give completely sharp estimates. One reason for that in higher dimensions is that there are some questions in higher dimensions about how much tubes pointing in different directions can overlap that go under the name of the Kakeya conjecture, and they're notoriously hard open problems. So that's one reason that people tended to feel one could not get sharp estimates that way. And it's also not at all clear from what I said that this should be capturing all of the information that you need to get sharp estimates for this problem that feels very number theoretic. And that was how people felt all the way until Bourgain and Demeter did their first paper. And what was new in that paper, what was really surprising, was how much leverage they were able to get by looking at the problem at many different scales. So just to carry out the plan I suggested so far, we only needed 2 scales. We cut the parabola into some pieces theta, and then we add up all of those pieces. But their argument involves many scales. So there are some thetas that are inside of some taus that are inside of some gammas, and you have hundreds of different scales. Or let's say you have s different scales, and the estimates become good in the limit as s goes to infinity. And it was really surprising to me, and I think to many people in the community, just how much leverage and mileage you get by incorporating information from all of these different scales. And so what I'd like to do in the rest of the talk is to try to explain what information from different scales we're looking at and sort of a little bit about how it fits together. Okay, which is a challenging thing, and so the approach I decided to take is just to work out one example and to point out in this example the different features that the proof needs to notice, the proof does notice, and take advantage of. All right. Okay, so in the example, there's just going to be one tube in each direction. So I'd like to think of tau 1 as being green, and I'm going to draw different green, the different f theta 1 and f theta 2 will all be green, and we'll think about how they add up to tau 1. And that would go like this. So this is where f theta 1 is big, and then f theta 2 is big on another rectangle in a slightly different direction. And we're going to add them up and think about what f tau 1 could look like. And f tau 1 will only be really big in the places where both the theta 1 and theta 2 are big. So that's some region like that. Okay. And then within that region, the worst thing that could happen is we could add them up and bound it with the triangle inequality and with orthogonality, and it could focus and be really tall in a somewhat smaller subset of this dotted rectangle. So it could look like that. And these dark green rectangles are where f tau 1 is big. Cool. So that's the effect that we already talked about. But now let's try to incorporate another scale. So we do the same thing for some f tau 2. So let's put tau 2 over here. We do the same thing for f tau 2, and then we're going to think about what happens when we add f tau 1 to f tau 2. Right, great. OK, so f tau 1 is constant on some tiling, which is the tiling of tau 1 star. And tau 1 star is littler than theta star. Let's look at our picture. So you can see from this picture, this dual picture, that the smaller theta is, the bigger the dual rectangle is. And theta is smaller than tau, so the dual rectangles of tau are smaller. And actually, the way that works out, if you check, is that there's a natural scale of the size of the intersection of two of these guys. And that's illustrated in this dotted line. But the dual rectangles to tau are smaller than that. This is the size they naturally are. OK, now what happened here? We added up several f thetas. And on each of these rectangles, each f theta had constant norm, but they're oscillating at different rates. And so when we add them up, we want to understand how much they may focus. And so we have the triangle inequality, and we also have orthogonality. Something I didn't say before is that the different f thetas are not just orthogonal on the whole space. They're morally also orthogonal on this little rectangle. So we can bound that. Actually, this bound may be lossy, but what we do in the proof at some bottom stage of our induction is we do just bound it using orthogonality and the triangle inequality, like we showed at the beginning of the lecture. And so that allows the possibility that that sum focuses on a small subset of the rectangle. And the most extreme way that it could look is like this. OK. So if I do that with the tau 1 and I do the same with tau 2, I get a picture like this. OK, so now I'm going to draw what happens when we add those. So when we add up the theta 1s to get tau 1, we get a chain of rectangles kind of like so. And when we add up the theta 2s to get tau 2, we'll get a chain of rectangles going that way. And it will look like so. OK. OK. Now when we add the tau 1s to the tau 2s, one thing that we notice is that a green rectangle and a red rectangle don't intersect very much. That's going to help us. That's the effect we already talked about. But there's something else we could notice about this picture, which is very important. This picture does not look like this. So if I just knew that there were 3 little skinny green rectangles and 3 little red rectangles at the given angles, the worst way they could intersect is like that. But that doesn't happen in this example. They actually are like this. And this red rectangle doesn't meet anybody green, and this green one doesn't meet anybody red. And that gives us better estimates. That happened because of something that you can see in this picture. So I'm going to try, this picture is in danger of becoming very messy, to copy this into that picture so you can see better how they're related to each other. the three green rectangles are something like this. Oh, sorry, green goes the other way. The three green rectangles look something like this. And the three red rectangles look something like that. Yeah. And the reason that this red rectangle is safe, this red rectangle here, the reason that it's safe from being intersected by anybody green is that already at this bigger scale, this little red rectangle was in a region that nobody green is going through. Okay. So the point I wanted to make is that we want to visualize the different f taus and estimate how much the relevant rectangles intersect each other. And we get some information about that by looking at the small angle intersection between the greens. But then we get some extra information about that by looking at the large angle intersections between the greens and the reds. And in the full story, there would be...
They have like 9 points of intersection.
What's that?
Why can't they all intersect? They have 9 points of intersection. Or they all sit.
Yeah, good. So Andre's question is, why not three greens shoulder to shoulder and three reds shoulder to shoulder the other way? Like that. This is even worse than the picture there that I said doesn't happen. This would be a nightmare. Yeah, good. Yeah, so this doesn't happen because the different f theta j's are already are already orthogonal on small balls of the following shape. So we can see it. Okay. Let me pause. It's clear to everybody what is the question? Okay. So the point is that at this moment here, we got one green rectangle at each height. We didn't get green rectangles all the way across there. And that happened because the different f thetas were already orthogonal to each other on each of these boxes. So on each of these smallish boxes, we can perform the analysis that we did at the beginning with the L2 norm and the L infinity norm. And so the worst case scenario is that on each box, the function focuses as much as possible. And we get a picture like that. Okay. So I think it's just about time to stop. I just wanted to summarize by saying that the proof takes into account information from a lot of different angular scales, as well as then taking account of a lot of different length scales, and puts that all together in a systematic way. And remarkably, it's possible that way to prove sharp estimates. Okay, thank you very much.
I think we have time to take a few questions.
Someone here? Yeah.
Go for it.
This is I think, but that's not the way this decoupling is usually formulated. It's usually formulated by some technically seeming state involving various LP norms. Can you relate how the structure is translated to these, is reflected in these formulas?
Yeah. Okay, so maybe I repeat. So the question is, if you look at the papers about decoupling, they have some equation, some LP norm of something is bounded in terms of some LP norms of other things, and how is that related to what we've been talking about? So I think a reasonable thing to do in a talk like this is to state what a decoupling inequality is. So here's the decoupling inequality written in terms of LP norms. So theorem, if the support of f theta j hat is contained in theta j, so theta j's and tau are as above. These arcs of a parabola merged into a bigger arc of the parabola. So if we have that, and if the f tau is the sum over theta j and tau of f theta, then the L6 norm of f tau is bounded by, there's a fudge factor, which is the number of thetas in tau to the epsilon, like the n to the epsilons that we've seen before. And then we have sum on theta in tau of f theta, L6 squared to the 1/2. So this is the decoupling inequality. And in some sense, the new point of view that I think was useful for studying this problem, well, I don't know if this was really new, but part of the point of view that I think is useful for studying this problem is instead of focusing on starting with the individual frequencies and just ending all at once with the function, let's focus on what happens when we take some pieces of the sum and add them up to make a bigger piece of the sum. And that operation is sort of more general, and so it's better for doing induction. OK, now the actual question was, what is the relationship between something like this and a picture like that? So I like to think of this as being approximately the sup over different heights lambda of the volume of the set where f tau is bigger than lambda to the 1/6 times lambda. This isn't exactly true, but it's true up to factors that are smaller than that. And so it's about how big is the region where f tau is big. And we're relating that to how big is the region where each f theta is big. And so the understanding that is based on how the regions where f theta is big overlap with each other, and then how much cancellation or not cancellation. So what happens on each of those overlapping regions? How much bigger is the sum than the individual f thetas?
So what is the significance of the number 6 there?
Yeah. Right. So let's put a p here for a second. And this is true for p between 2 and 6, 2 being obvious, 2 being just orthogonality. And then it becomes false when p is bigger than 6. Why? Suppose for a second we put L infinity. If this was true, it would say the biggest that f tau could be is like the biggest that f theta could be, suppose they're all the same as each other, times the number of thetas to the 1/2. And that's obviously wrong, because you can pick one point and arrange that all of the f thetas are positive real at that point, and then they add up linearly. So there has to be some threshold where this stops being true. And you can make an example which is based on that example with 1 point. So you arrange the f thetas are all big at 1 point, and you add it up, and you check that in that one example, this is true for p up to 6 and not above 6. And the significance of 6 is that that one example is the worst scenario that can occur.
One should be able to unravel that to say if you got a bound like that with p higher than 6, and you get a bound for the graph that's smaller than n cubed, and n cubed is the trivial lower bound. Remember?
Yeah, that's right. Yeah, actually another significance of 6 is that if the exponent that comes up in Wiener-Gradach is 2s, and so this corresponds to s equals 3 and k is 2. And that's the critical value for k equals 2 that we talked about before when we had the number of non-diagonal solutions is about the number of diagonals.
Okay, let's thank Larry again.